6.2 standard normal distribution. Standard normal distribution is a continuous distribution whose we will have a new point of view compared to what we have learned so far, a slightly different point of view. Here's the idea. Let me get the picture from, so that I don't need to keep on drawing normal distribution. Give me a second. Okay, you are now. Normal distribution looks like this. Standard normal distribution will have the mean, let me use another color, will have the mean equals to 0. And basically, this is what will happen. When the distribution is continuous, then the probability of an event is computed, or is computed by finding the area under the curve, density curve. Now, I will explain about that a bit further, but let's take a look on standard normal distribution first. Now, standard normal distribution, let me call that SND, has a curve that is bell-shaped. It looks like this, the one you see here. The one you see here, it looks like a bell shape. Okay, and the area under the curve is 1. So if I compute the total area under the curve, the total area here is 1. And then next, it's symmetric around the mean, and the mean mu is equal to 0. This is the mu equals to 0. Okay, now, and then furthermore, the domain is all real numbers. In other words, this curve actually goes indefinitely far to the right and to the left, okay? And the curve never cross x-axis, never touch x-axis, okay? It's just so small such that the area is basically zero. But the domain is actually going to positive infinity and going to negative infinity. Now, here's the thing. Standard normal distribution is a very important normal distribution that we will focus on. Later on, other normal distribution will basically boil down to this standard normal distribution. Mm, Standard normal distribution, standard normal distribution is denoted, not usually, is denoted by capital Z. Okay, denoted by capital Z. This is the only distribution in probability and statistics that reserve a special random variable notation, and capital C will be a random variable that will not be used by any other random variable, any other distribution. Okay, now, and the standard normal distribution has mean, the mean is 0 and standard deviation equals to 1. Now, we will see the importance of standard deviation equals to 1 much later. Okay, but for now, we don't worry about that. Thomas, I still don't get what it has to do with probability. Now, that's what we are about to do. Okay, suppose, for example, we want to find the probability that Z is less than 1. Now, what does it mean? Now, we will do the following. That's the normal distribution. Okay, the mean is 0 here. Okay, now we want to find the probability that the normal distribution, the distribution is less than 1. Then we will denote 1 on the position of 1 on this curve. Say, let's say this is 1. This is Z equals to 1 here. Now, then the probability that C is less than equals to 1 is basically to find the area to the left of 1, less than 1, right? Yeah, to the left of 1, the area under the curve, to the left of 1. We want to find the area here. Okay. Now, there are two methods to find the area of standard normal distribution. One method is by using a table. Okay, let me write that as a warning. Now we will use calculator to compute the probability. Of standard normal distribution and any other normal distribution. The reason I want to write this down because I think around 3 years ago, I still use table method. Right now, we will use calculator method. Okay. Now, then how do we compute the probability that C less than 1 by calculator? We will write the notation first. The notation will be normal CDF Okay, and then negative 1 E99, comma 1, comma 0, comma 1. Now I will explain what this notation means. Basically, this is what happened. The interval that we need to deal with is from negative infinity up to 1. That's from negative infinity up to 1. Now, the problem is we don't have negative infinity in calculator. We don't have this negative infinity in calculator. So we will replace that by negative something big, some number very, very big. Okay, and we will replace that by negative 1 times 10 to the 99. We'll replace that by that. Now, the thing is, to type that 10 to 99, when we use calculator, we will use uh, E for exponent 99. Okay, now I will teach you how to type it in later on calculator. Now you will see that the first two numbers here actually represent the interval. The first two numbers there actually represent the interval. Now then, this number here represent the mu, the mean of distribution, the mean of the normal distribution. Because it's standard normal, then the mean is 0. And the 1 here is for the standard deviation. Because it's standard normal distribution, then the standard deviation is 1. Okay, so the notation to find the probability of standard normal distribution will be normal CDF. The first two numbers will be the interval. Okay, of course, the one on the left is the left boundary, and then the one on the second number will be the right boundary. The third number is the mean. The last number is the standard deviation. Okay, let's take a look on how to use calculator to punch it in. Give me a second. I want to punch normal CDF. The position of normal CDF is with that distribution. Remember when we did the binomial distribution and Poisson distribution? Something that you will see next week. Okay, now it will be in the same category. I go to second distribution. Now, normal CDF is number 2, the second one here. Okay, so I will get normal CDF, enter. Now, they will tell us the lower bound. Now, the lower bound, you may wonder, Thomas, how do we punch this, negative 1 E99? Let me clear that first, and then I show you how to do it, okay? The negative, not the subtraction sign, no, you need to use this sign here, negative 1 times, okay, or if you don't use that times, you are fine. Now, where is that E99? The E99 is this one here. I wonder if you can see that. On our calculator, they write it as double capital E. It's double capital E. But when you type it second EE, you will see just capital E, 99. Oops, sorry. Well, that's okay. Now, then I go on. The upper bound will be 1. The mean is already 0. The standard deviation is already 1. I go ahead, paste it, enter. Oops. Duh. let me repeat again. I think I have extra 99 there. CDF. I need to change this one. Negative 1 is 99. Down, down, down. So the normal, the probability will be 0.84134. 84134. Now, after you write the calculator notation, then you write the probability, the value 0.84, 84 what? 134. It means the area, the yellow area here, the area of the yellow region here, the area is 0.84134. Now the thing is, under continuous distribution, the probability of an event is being computed by finding the area under the density curve. Okay, this is the density curve here. Okay, that's the density curve. Okay, so the area will be the one covered by whatever the effect you want. Okay, now, by the way, going back to the notes. So going back to the note that we replace negative infinity by negative 1e99. We will replace infinity by 1e99. Okay. Now, let's try a couple more examples. Let's see example B. Find the probability that C is between negative 1.23. C is between negative 1.23 up to, let's say, 1.74. So from negative 1.23, that's to the left of 0, and C equals to negative 1.23 to 1.74, let's say approximate here. C equals to 1.74. So we want to find the area under the curve between C equals to negative 1.23 to C equals to 1.74. Now, if you remember, the interval notation for this will be, negative 1.23 up to 1.74. Okay, well, I suppose to use bracket here, but you will see that either it is equal or including the endpoints or not including the endpoints. The notation will be the same when it comes to continuous distribution. Okay, let's see. How about the notation, the calculator notation? That will be normal CDF. Okay, and then the interval is from negative 1.23 to 1.74. That's negative 1.23 comma 1.74. Okay, and then the mean is 0. The standard deviation is 1. Okay, that's the mean. That's the standard deviation. Okay. In 8.3, then you will see this mu, the mean and standard deviation will change. What does CDF stands for? CDF stands for CDF stands for cumulative. Is it double M? Should be double M. Huh? I don't think so. Well, anyway, cumulative density function. That's what it stands for. Sometimes when it comes to discrete distribution like binomial or Poisson, then it is called cumulative distribution function. But for continuous case, we call that cumulative density function. Okay, what the CDF stands for? Now, of course, if you ask what CDF stands for, that's cumulative density function or cumulative distribution function, then you may wonder what PDF means. When we did the binomial PDF, Poisson PDF, or here, we will never use it, but we have that function, normal PDF. PDF stands for probability density function. Distribution function. Okay, again, they use the word density if the random variable is continuous. They use the word distribution if it is discrete. Okay. Now, you may wonder about why we call standard normal distribution is continuous distribution. There are a lot of continuous distribution, by the way. Okay, there are a lot of continuous distribution. Now, but how do we know that this distribution is continuous and the other distribution is discrete? Let me set aside some time to explain that difference. Okay. Actually, if you watch the lecture video, they actually explain it quite well. But here's the thing. If we look back to binomial distribution, we know that the outcomes are possibly 0, 1, 2, all the way to n. Okay, Poisson distribution actually is very similar. Poisson distribution, we call that a discrete distribution because the possible outcomes are 0, 1, 2, and up to infinity. Okay, now how do we know a distribution is discrete and not continuous? For discrete, both of these are discrete. Is when we can find two outcomes without any outcomes in between. Let's say, for example, the number of, if we toss a coin 5 times, how many tails we can get? Well, we can get 0, 1, 2, 3, 4, 5 tails. Okay, now the thing is we can find two outcomes, let's say 3 and 4, without any outcomes in between. Okay, so you may have 3 tails, you may have 4 tails, but you cannot have 3.5, for example. Okay, now that's what we call discrete distribution. If you can find two values of the random variable that has no value in between. Okay, now we cannot have 3.5, we cannot have 3.7, we cannot have 4.1, we cannot have 1.3. Okay, now I'm not saying that the numbers has to be integers. No. It is possible that the outcomes are not integers, but still it is discrete. For example, the shoe size. Let's say, for example, we have size 7, we have size 8, but we also have 7.5, right? For example. Okay, so between 7 and 8, you can find something in between. However, between 7 and 7.5, there's nothing in between. There's nothing in between. You cannot find a shoe size 7.4. Okay, so shoe size, when you buy a shoe, the size is actually a discrete distribution. Okay, because even though we have the half size, but we don't have a quarter size, for example. Now, how about continuous distribution? Continuous distribution like normal distribution, as you can see later on. Continuous. Is for every two outcomes, we can find an outcome in between. Let's say, for example, my height is 5'10", and then somebody else's height, let's say Tim's height, is 5'11". Okay, then the thing is, you can find an outcome. There is possible an outcome that is 5'10.7". Okay, so imagine that on a number line. Imagine that on the number line. That's why we call it continuous. Between 5'10", to 5'11", okay, whatever number you pick in between, that's a legitimate height. Okay, so it is possible somebody have height 5 feet 10.7 inches. It's possible. Okay, in fact, even in this interval, for any two outcomes, we can find an outcome in between. So even if you make it this interval, you can find somebody whose height is 5'10.4", for example. Okay. Now, when we say it's continuous distribution, it means the outcomes may be any number in between two numbers. Okay, that's what we mean by continuous distribution. While for discrete distribution, the outcomes only certain number, but maybe not in the, and not in between. Okay, that's the difference between discrete distribution and continuous distribution. Therefore, the way we compute the continuous, the probability for continuous distribution and discrete distribution will be different. Okay, now that's the difference between discrete distribution and continuous distribution. Let me erase this not to interrupt our discussion about this. Okay, now let's go back to this question that we didn't finish. Can anybody compute that for me? We get, that's right, I get 0.84972. Second, I reply one question. Okay, let's try more. Let's try more. Let's try more. You do this time. Okay, try to sketch the curve first. Try to sketch the curve first, the one that I did, here. Okay. Part C probability from 1.58 up to 3.1. Okay, you try the calculator notation first and then the value you get from calculator. Let me know if you want me to show you how to use calculator again, but I believe you should all try it at least, okay? So the notation here will be normal CDF 1.58 for the left fence, the lower fence. The upper fence is 3.1. The mean is 0. The standard deviation is 1. Then when I press enter, I get 0.05609. It's 0.0. It's not 0.5. Yeah, it's 0.0. Okay. Actually, then you will see the following. What is the probability from 0 to infinity when C is greater than 0? C is greater equals to 0. If you think about it, this is 0. So greater than that will be exactly half of that distribution, right? Because the other side here is exactly the same symmetric. It's the same shape. The same shape, the same size, just the other way around. Okay, so I hope even without calculator, you know this is 0.5. This is exactly what happened. But you can try using calculator normal CDF from 0 up to infinity E99. The mean is 0, the standard deviation is 1. You can try to confirm. I believe you'll get 0.5. Okay. Now, I would like you to take a look on problems from our textbook on page 258. Page 200. On page 258, I would like you to do question number 12, number 16, number 20, and number 24. I'll give you an example. I would like you to first write the probability notation. And then after that, the calculator notation. And then the probability value from calculator. Let's say, for example, I do number 14. Number 14, it says that greater than 1.96, greater than 1.96. So the probability notation will be probability C greater than 1.96. Now, how about the calculator notation? Our calculator notation, let me do the curve, what the curve look like first. 1.96 is, let's say, is here. This is C equals to 1.96. I need the one greater than that. Okay, so it will be normal CDF. The left bound is 1.96. The right bound is E99. The mean is 0. The standard deviation is 1. Now, then you punch into your calculator. Let me punch into mine. I think that's 0.05, 0.025, but I may be wrong. Yeah, that is 0.024998. But that's 6 decimal places. In 5 decimal places, that's 0.02500. Okay, now that's how I want you to show the work. Let me give you, let's say, how many minutes? Maybe around 6 or 7 minutes. Okay, 6 or 7 minutes. Yeah, let me ask you to do this first. Okay, sketch the graph whenever possible. The reason I want you to sketch the graph so that you can see what the interval be. The first two numbers, okay? I need you to be able to imagine that from the graph. Okay, right now it's 9:41 on my computer. Let's come back at 9:50. But you do this, okay? You do this. You do this. Okay, let's start again. Here's what we have. The given, the event, find the probability. So knowing the event, we'll find the probability for number 12. The event is less than 2.5. Again, we are still talking about standard normal distribution. Okay, if that's the event, what is the probability notation? Z is less than 2.50. calculator notation, that's normal CDF. That's normal CDF. Oh, let's see what the distribution looks like. Okay, less than 2.5. Less than 2.5. So if this is 2.5 here, C equals to 2.5. I need the one less than that. So anything from negative infinity up to 2.5. I need the one in this region, which means again from negative infinity up to 2.5. Negative infinity up to 2.5. So my normal CDF first one is negative E99, comma 2.5, comma 0, comma 1, which when I use my calculator, I get 0.99379. That's for number 12. Number 16. The event is greater than 1.96. So the probability C is greater than 1.96. If I want to know what it looks like on the curve, 1.96 is, let's say, somewhere around here. That's 1.96. I need the event that is to the right of that, greater than 1.96.
Professor, it would be greater than negative 1.96.
Oh, great. Oh, thank you. So greater than negative 1.96. Negative 1.96 approximately here. I need the one to the right of that. Still to the right, but we start from different C-score. So from negative 1.96 to positive infinity, get the negative here. Okay, so that's the curve. This is equals to normal CDF negative 1.96 E99 0 1. That will be, if we round to 5 decimal places, that's 0.97500. Okay. Now in your quiz or in your test, you don't need to draw this curve. I just need the probability notation, calculator notation, and the probability value. That's good enough. Okay. Now, but Thomas, why do you give the curve here? Okay, so that you can visualize how I get. This the first two numbers in the parentheses here. Okay, because it refers to this interval that we are looking for. Okay, that's for number 16. Let's go further. Number 20? between 1.05 and 2.05. So probability at 1.05 less than capital C less than 2.05. That is normal CDF 1.05, 2.05, 01. Will be 0.12668. You can sketch the graph or the curve if you want, but it's not needed actually. Okay. And what is the last one? Number 24. Yeah, number 24. Between negative 1.80 and 2.08. Probability negative 1.80 less than capital C less than 2.08. That's normal CDF negative 1.80, 2.08, 1. And 0.94531. Is it what you get? Somebody give me the answers. Oh. Oh yeah, that's number 22. Thank you. Thank you. This is number 22. Number 24. Between negative 3.9. Between negative 3.90 and 1.50. That's probability negative 3.90 less than C, capital C, less than 1.50. That's normal CDF. Negative 3.90, 1.50, 1. It will be 0.9331. Okay, now that's when we know the event. You need to find the probability. Then you need to do it in the following steps. You need to find the probability notation first, and then calculator notation, and then the probability value. Okay, now some little notes on calculator. Okay, our calculator probability of left fence less than standard normal distribution less than upper fence is equal to normal CDF left fence, comma, upper fence, comma, 0, comma, 1. Now, if you use TI-84, very likely the view will be like the one we saw earlier. Let me share what we saw earlier. On this calculator here, when we punch normal CDF, now it will give us this. It will give us this window here. Okay, and then you plug in the lower fence, upper fence, the mean, and the sigma, and then you paste it. Okay, and then let's say I still use this one. Now then it will give you this interval, right? Now some calculator, however, you don't need to, they don't really guide you to get these numbers. You can just type normal CDF right away and something comma something comma something. Now the thing is you may see some people don't even write this too. Okay, of course, if you use TI-84, then the mean has to be set to be 0, and the standard deviation has to be set to 1. Okay, but when it is standard normal distribution, only for standard normal distribution, let me say it again, only for standard normal distribution, then what we wrote earlier can be written without the last two numbers. So you can write it as LF, lower fence, upper fence, and that's it. Okay, yeah, because our calculator is set to the following default. The default for normal CDF is mean equals 0 and sigma equals to 1. Okay, so for some older calculator, you can just punch it right away, normal CDF, lower fence, upper fence. Okay, yeah. But if you use TI-84, you don't need to worry about that. Well, that's, in fact, I think I should say, if you use TI-84, you need to worry about that. You need to worry about lower fence, upper fence, the mean, and then the standard deviation. Okay, now let's summarize what we have learned so far. We have learned that given the event, of course, there's something called C-score there. These are the C-score. Okay, those are the C-score. Then find the probability. And when they give us the event, they give us this what we call C-score. Okay, Thomas, what is the C-score again? C-score is the upper fence, lower fence. Now on the curve, this is what we call C-score, lowercase z, not capital C. Capital C is the random variable. Now, then we need to go backward. Suppose we change the question. Given the cumulative probability find C-score. What does it mean, Thomas? It means the following. Suppose we know the area. Suppose we know the area to the left. That's cumulative. Suppose we know the area to the left. Yeah, up to certain C. The question is, what is this? What is the C score if the area to the left of that C score is given? Okay, that's what we want to find out. Calculator work. Okay. Let me go back a little bit. Somebody have a question. Suppose I want to do number 24. Okay, suppose I redo number 24. Probability between 3.9 to 1.5. That's normal CDF negative 3.9. That's the left fence, the lower bound. And 1.5 is the upper bound. Now, how to use calculator for that? Let's go to our calculator. I will do normal CDF. So second distribution, normal CDF. Boom. Okay, now, what is the lower bound? Negative 3.9, as I remember. Negative 3.9. Enter. The upper bound 1.5. Enter. The mean already 0. The standard deviation already 1. So I'm ready to go. Okay, so 0.93314. Great, good. Let's continue. What we have earlier, yes, well, if we are given the probability, the cumulative probability means the area to the left of a certain C-score. How do we find this C-score? Okay, let's write the notation first. The notation is this probability. Let's say for example, if the area to the left, which means the probability the cumulative probability is 0.75, let's say, then find the C-score. Okay, first, what is the probability notation? Probability that the random variable, capital C, is less than C-score C. Okay, so this capital C here is the random variable, and this lowercase c here is the C-score. Now, to avoid confusion, I will call the C-score instead. I will use K. Okay, let me use K here to avoid confusion between capital C and lowercase c. I will use K for my C-score. The probability that's the random variable is to the left of K is 0.75. Now find K. Now to find K, I will use inf norm. That's the function, as I know, that's right below normal CDF. It stands for inverse norm. Okay, and the notation in parentheses will be 0.75. Okay, now this 0.75, is the area to the left. Area to the left. And then comma 0, comma 1. Okay, so again, this is the probability notation. This is the calculator notation, and then later on we'll find the K. K equals what? Let's go to our calculator. I want to find the C score, the K, such that the area to the left is 0.75. Second distribution. Now you see number 3 is inverse norm. Now what is the area? The area here again is cumulative area, always area to the left, always area to the left. That is 0.75, and by default, the mean is 0, the standard deviation is 1. Enter, I get 0.67449. 0.67449. Going back to my note, that's 0.7449. Okay. Let's do one more. Suppose I want to find the C score such that the area to the left is 0. Let's say 947. Pictorially, the area to the left is, so find the K here, such that the area here is 0.947. Now first, what is the probability notation? Probability that C is less than K to be 0.947. It has to be the area to the left. Then we can use our calculator. So K equals to inverse norm 0.94701. Okay, again, it's area to the left. The second number is the mean. The third number is standard deviation. And then what will K be using our calculator? You do it, I do it too. I get 1.61644. This guy here is 1.61644. Okay. Let's do a little variation from there. Suppose I go the other way around. find the C-score such that the area to the right is 0.05. The area to the right is 0.05. I want to find the C-score, the K, such that the area to the right is 0.05. That's 0.05 there. But our calculator cannot compute, cannot find the K if we know the area to the right. So notation-wise, this is probability that C greater than K is 0.05. But again, our calculator cannot deal with that. So I need to change this into probability that C less than K. Now, if the area to the right is 5%, 0.05, what will the area to the left be? The area to the left will be 1 minus that, right? 1 minus 0.05, that's 0.95. Okay, that's 0.95. Now, by the way, we usually call this number, this K here, we usually call this K also as P95. That stands for 95th percentile. In other words, the area to the left of that, the area to the left of that here, the area here is 0.95. Okay? If the area is to the left is 0.95, then the C-score, the K, is called P subscript 95. Okay, now I don't really use this in my class. I don't really use this notation, but if you read the textbook, they use that. And that's actually, even though not common, but sometimes used even in our daily life. Okay, so our K here, which is our P95, is equal to inverse norm of 0.9501. Now that K will be 1.64485. But you can use your calculator to confirm. Okay, now that's for this standard normal distribution. Now let me go on to normal distribution in general. 6.3 normal distribution. Now, normal distribution is actually the distribution we see most often in our daily life. The second is binomial distribution. Normal distribution is the distribution that we encounter the most in our daily life. Now, let's do some notation definition. non-standard normal distribution. Is a normal distribution with mu not equals to 0 and or the standard deviation is not equals to 1. Okay, now that's for non-standard normal distribution, which we usually just say standard normal, we just say normal distribution. Okay, now because it is non-standard, then we can use X for that, just like other distribution. And the notation will be normally distributed. The first number is the mu. The second number is sigma squared, however. Okay, not the second number is the variance, not standard deviation. Yeah, there's some little confusion later on between the notation and the calculator notation. Okay, now, so if we think about this, so that standard normal distribution is basically a normal distribution with mean 0 and variance 1 squared. Or sometimes we just call that normal distribution 0, 1. That's for standard normal distribution. Okay, but in general, normal distribution has mu not 0 and the standard deviation not 1. I go ahead with one example. Let me do this example first. Let X be normally distributed with mean equals to 100 and standard deviation 15. Okay, and then I cannot use capital C anymore because this is not standard. This is not standard. Okay, because the mean is not 0, the standard deviation is not 1, then I cannot use capital C because it's not a standard normal distribution. Suppose I want to find the probability that X is between 90 to 120, let's say. Now then the calculator notation will be, let's do the curve first. Now, normal distribution, just like standard normal distribution has a very similar curve. Has a very, very similar curve. Okay, the difference is the mean right now is not 0. The mean right now is 100. Okay, so the curve will be symmetric around that 100. We are now interested to find the probability between X equals to 90 to X equals to 120. Notice that I don't use C anymore. I use X right now. Okay, because I cannot use lowercase c because it's not standard normal distribution. Okay, it is non-standard right now. Now, we want to find the probability of this area here. Now, if you are good with the notation that we had in 6.2, then the one here should be easier. Okay, why? Because we just continue. That will be normal CDF, the left fence, the right fence, right, from X equals to 90 to X equals to 120. Now, the new stuff is the third number, the mean is 100. The mean is 100. Okay, and then the variance, the standard deviation is 15. Okay, the standard deviation is 15. Not 15 squared, just 15. Not 15 squared. Not 15 squared. Okay, we take the 15, the standard deviation. Now then you can use your calculator to compute. Value 120, 100, 50. I get 0.65630. Okay. Now, nothing much really to say anymore about the notation, except that, again, I cannot use capital C because it's non-standard. This is non-standard. Capital C only for standard normal distribution. For other type of normal distribution, you cannot use capital C. Okay, we usually use capital X for other distribution. Okay, and the notation for normal distribution is N. That stands for normal, parenthesis. The first number is the mean. The second number is variance squared. Okay. Now then, the way we punch into calculator is very similar, if not similar, the same to what we have before. Now, the focus of this section 6.3 is actually on the application. So let's do some application problem. The distribution I showed you earlier is actually one well-known distribution for our IQ score. So let's take a look, for example, in your textbook, please take a look on page 266. On page 266, we'll do problem from 5 to 12. Actually, I will just do number 6, number 8, number 10, and number 12. Okay, we'll do this distribution. Now, this four questions here, they are related, but pay attention to the difficulty that you may encounter later on. The difficult part will be, first, you need to identify the normal distribution, the mean, and standard deviation or variance from the word problems. And then second, okay, you need to write the notation, the distribution notation. And then write the probability notation. And write calculator notation. And then you use your calculator to find the solution. The probability value. Okay. Now the thing is we have learned this part. We have learned this part. The one that is new for you will be this. Unfortunately, that requires some reading skill. Okay. Now, and I don't teach you reading. You need to be able to understand the English yourself. Okay. Now, from passage between number 5 to 12, assume that adults have IQ scores that are normally distributed. Okay, so we are talking about IQ score. Let's define the random variables. Let X be an adult IQ score. Now they say this adult IQ score is normally distributed with mean of 100 and standard deviation of 15. Okay, now remember the second number in the distribution notation. The second number in this normal is variance, not standard deviation. That's why I write it as standard deviation square. Okay. Now, when I say identify the normal distribution from the words, okay, and write the distribution notation, I refer to this. I refer to this. Okay. Now then, number 6. Number 6, find the probability that a randomly selected adult has an IQ greater than 131.5. That's the passage. That's the question. We want to find the probability that an IQ score is greater than 131.5. Greater than 131.5. So from 131.5 and greater, which goes to infinity, right? Okay, so then what's the calculator notation? That's normal CDF 131.5 up to infinity. I use E99. The mean is 100. The standard deviation is 15. Okay. So this is the left fence, right fence from the interval. This is the mean. And this is the standard deviation. Okay. Now then, using calculator, I get 0.01786. Am I okay? Now let me ask you to try number 8. I think number 8 is very similar. Find the probability that a randomly selected adult has an IQ between 110 and 120. Like before, I want you to, we already have the distribution notation. We already have the distribution notation, the blue one here, right? Okay, we already have that. Now I need you to go ahead with the probability notation, calculator notation, and the solution. Let me give you maybe 1 minute for that. So the probability notation, probability that the IQ score, which is our X, is between 110 to 120. That's the probability notation. Now calculate notation. Normal CDF. The left fence is 110. The right fence is 120. The mean is 100. The standard deviation is 15. I get 0.16128. Thank you. That's for number 8. Okay, very similar to what we did before, right? In fact, it's very similar to standard normal distribution, except that now the mean is not 0, now the mean is 100, and the standard deviation is not 1, now it's 15. Okay, while the interval is still this. Okay, yeah. You need to know how to write the probability notation, and after that, it's just the calculator work. Number 10. Number 10, find P60. Find P60. Now, P60 is the K. Let me write it down. This is equals to the K such that the area to the left is 60%, which is 0.60. The area to the left is 0.60. Okay, so first, what's the calculator notation? Probability that x less than k equals to 60%. 60% in decimal 0.6. Okay, so k equals to inverse norm 0.6. The mean is now 100. The standard deviation is 15. Okay, because we are now looking for the k, looking for the c score. I'm sorry, the x score. We are looking for the value such that the area to the left is 60%. We are looking for the x value such that the area to the left is 60%. So we want this to be 60% here. Now what we need is to find this k. Okay, so we are given the probability. Okay, we need to find the k value. Okay, now then when you use calculator, inverse norm 0.6, 100, 15, I get 103.800 to 1. Or you can say that you write this first in your test. If you want to round it, then you can write it after, but write this first. Okay, so what does this mean? This means that the 60th percentile, if somebody's IQ score is 103.8, then 60% of the population has IQ score less than or equal to that. Okay, and 40% has IQ score greater or equals to this 103.8. Okay, now that's for number 10. Let me ask you to find, to do number 12. To do number 12. Find the IQ score separating the top 85% from the others. So, the top 85%. The top 85% means the area from the top. The area from the top is 85%. The area from the top is 85%. Area here is 85%. So we need to first find what is the area to the left later on. Okay. Then before you use calculate. Okay, let me give you 1 minute. Okay, the area from the top is 85%. So the probability that x is greater than k is 85%, which means probability that x is less than k is 15%, right? Is 15%, which is 0.15. So this k is also called P15, not P85, not P85. Okay, it's P15. Okay, it's the area to the left is 15%. So this is inverse norm 0.15, 115. I get 84.4535. 45350. If I round to 5 decimal places. Okay, and that's for this number 12. Let's go on. Let's go on. I will do number 14 and then number 16. Later on, I will give you, during the break, together with the break, I will ask you to do some problems together with your break as usual. Okay, number 14. Number 14 and number 15, number 16 relies on the information we have above. Above number 13. Above number 13, you see use these informations based on the data from National Health Survey. Okay. For number 14, it's about the height requirement for women soldier. Women's height are normally distributed with mean 63.6 inches and standard deviation 2.5 inches. So let x be a woman's height. This x is normally distributed with mean 63.6 and standard deviation 2.5. Now then, number 14. The U.S. Army requires women's heights to be between 58 inches and 80 inches. Find the percentage of women meeting that height requirement. The percentage equals to the probability, equals to the proportion. The probability or the proportion of a woman's height to be between 58 inches to 80 inches. That's why I want you to write this first. I want you to write this first. that summarizes a lot of information at once. That's equals to normal CDF 58, 80, 63.6 for the mean, 2.5 for the standard deviation. Normal CDF 58, 80, 63.6, 2.5. I get 0.9875. In percentage, that's 98.745%. Okay, that's the percentage of women meeting the height requirements. Now, the follow-up question, are many women being denied the opportunity to join the army because they are too short or too tall? So what is the probability of too short or too tall outside of that, right? And that will be 1 minus 0.9875. The probability of being too short or too tall, basically the probability not satisfying the requirement outside of that. Okay, that's why I use the complement probability, and that will be 0.01255. Now notice that this is less than 5%, right? Notice that it is less than 5%. And because the probability for that to happen is less than 5%, are many women being denied? Because it's less than 5%, then it is unusual. Okay, unusual, quote unquote, unusual, and therefore not many. Okay, that's for number 14. Now, how about number 16? Number 16A, what percentage of women are too tall to fit in the standard casket, and what percentage of women too tall to fit in standard casket? They say the standard casket has an inside length of 78 inches. Okay, now the question is, I will do the women, just the women part. What percentage of women are too tall to fit in the standard casket? Okay, so the question is the probability that X greater than 78, right? Probability of too tall means it's greater than the standard casket, okay, which is 78 inches. So then this will be normal CDF greater than 78. So that's 78, E99, 63.6, 2.5. Oh, all right. I get 4.21839 times 10 to the negative 9. It's this means 0.00, a lot of zeros, and then 4.21839, and the number of zeros here, 4 is at the 9th decimal place. We know it's at the 9th decimal place because this negative 9. Okay, so if we round to 5 decimal places, that's basically 0. That's basically 0. Okay, so very, 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 very likely that every woman will fit the standard casket. Okay, now based on those results, does it appear that standard casket size is adequate? The answer is yes. Okay, so we don't need to make it like super, super big, super, super tall. No, that's for part A. Part B, a manufacturer of caskets wants to reduce the production cost by making smaller caskets. What inside length will fit all men? Let me do all women. Yeah. Find inside length to fit all women. I changed that to all women except the tallest 1%. Yeah, I changed the wording, therefore the question, to all women. Okay, now we want to find what is the K such that only 1% of women taller than K. Now, but to solve this problem, I need to make it into less than K, which is 99%, right? If it cannot fit the tallest 1%, it means it can fit the shorter 99%. Therefore, K is equal to inverse norm 0.99, 63.6, 2.5. I get 69.41587. That's the answer. Okay, now I'm about to give you a break. Together with your break, I would like you to do some problem. I would like you to do number 16. Do number 16 again. Okay, but for the men's version. Men's version. Okay, let X be man's height. And you read the passage above number 13 to find the distribution for man's height. And then I want you to do number 16A, 16B for the men's version. Okay. And then after you're done with number 16, I would like you to do number 17. Yeah, number 17. Try to do number 17. Okay. Together with your break, let's say this question will take you 5 minutes. Together with your break, 10 minutes. We come back at 11:15. Okay, so part 16A, 16A, what percentage of men too tall to fit in the standard casket? That X is normally distributed with mean for the men right now is 69.0 and then the standard deviation 2.8. So probability that a man will not fit into the casket is Px greater than 78, that's normal, CDF 78, E99 in place of infinity, 69 for the mean, 2.8 for the standard deviation. Using my calculator, 78, comma, infinity, comma, 69, comma, 2.8. I get 6.53911 times 10 to the -4. So that is 0.00065. That's the probability for part A. Now part B, for a man not to fit into the standard casket. Part B, manufacturer wants to reduce production costs by making smaller caskets. What inside length will fit all men except the tallest 1%? Probability that it will be less than K equals to 99%. Maybe I write it properly first. Except 1%, right? So the tallest 1%. So it will fit, which means less than K is 99%, that's 0.99. So K equals to inverse norm of 0.99, 69, 2.8. That's K equals to okay, that's 0.9. Okay, 75.51377 inches. Okay, that's for number 16. Now number 17. I actually wanted you to do number 18, but anyway, they give the same informations. Okay, birth weights in the United States are normally distributed with mean this and standard deviation that. Okay, let me take care of that first. Let X be the birth weight. This X is normally distributed with mean 3,420 grams, so 3.4 kilograms approximately, and standard deviation 495 grams, approximately half a kilogram standard deviation. Now then, if a hospital plans to set up special observation condition for the lightest 2% of babies, the lightest 2% means at the bottom 2%. So I need to find that K, what is the cutoff such that less than that is 2%. Okay, so then K equals to inverse norm 0.02 3420 495. Okay, so that's inverse norm 0.023420.495. That's 2,403.39429. Okay. So if the birth weight of a baby is less than 2,403 grams, let's say approximately 2.4 kilograms, then they will put that baby on special observation, yeah, because of the underweight. Because of the underweight. That's for number 17. There are a lot more problems that you can do in this section here, but of course, most of them are applying the same thing again and again. Now, let me explain the difference between the what actually happens, the relationship between standard normal distribution and the common normal distribution. Maybe I write it here, extra. Something good to know. But if you don't know this, I think you should be fine to pass the class. Okay, but to get an A, I don't think so. So if you want to get an A, you better know about this. Okay, now relationship between Z, the standard normal distribution, and non-standard normal distribution. Call that X. Okay, here's the thing. We have normal distribution. Oh, where's my picture? We have that normal distribution X. Okay, let's call this normal distribution X. The mean may not be 0. Standard deviation is not 1, not necessarily be 1. Then I insert the standard normal distribution. This is C. Okay, the idea is as the following. Suppose we want to find the area to the left of some X. I put this down here. Okay, suppose this is X, this is the C score. Okay, now the area to the left of that X of a certain value, when we try to find that area, what we will need to do first is to convert this X here. We need to convert this X here to be a C score. So what our calculator is doing, actually, when you punch in those numbers, our calculator actually convert that into C score first. Our calculator actually convert that to C score first. Okay, now then from that C score, they use their internal computation. Okay, so suppose we have that X is normally distributed with mean mu and variance sigma squared. Okay, and then we want to find the probability that X is less than that lowercase x. I think I don't want to use X. Let me use K here. Yeah, I will keep that X. I will keep that X. I will keep that X. But I will make it like this so that you know which X I'm talking about. Okay? Now then, what our calculator doing, and if you look at my old tests, like prior to 2014, at that time I still ask them to use a table. Then the way they find the C-score is by using that X minus whatever the mean over the standard deviation. Okay, so this is the X, this is the mean, this is the standard deviation. Now then the C-score, oops, becomes so dark. Let me erase that. The C-score here, okay, is actually computed by using this formula. Okay, so what our calculator is doing, is actually computing this. That's equals to probability of C less than that C here. Okay, now my table method, I require them then to compute this manually. Okay, to get this. This procedure is called standardizing. And then from here, they will use table. Okay, now, but you don't need to use table anymore, so that you don't need to compute it this way. However, this formula is still a formula I strongly recommend you to memorize. I strongly recommend you to memorize this formula. This is a standard C-score formula. This is a C-score formula. Formula for C-score. Okay, which if you think about that, this C-score actually means the C-score itself means the number of times, number of standard deviation above the mean. Yeah, if it is negative below, if negative. Now, if you remember the usual interval, recall usual interval is the mean minus twice standard deviation up to the mean plus twice standard deviation, right? Now that's because the C-score of the data has to be between -2 to 2 to be considered usual. Okay, so how do we find out this usual interval? Is by looking at the C-score of the data, and the C-score has to be between -2 to 2. Okay, now that corresponds to this mu minus twice standard deviation, mu plus twice standard deviation. Okay, so for example, some fast question. For example, is an IQ score of 150 considered unusual? We know that IQ score is normally distributed with mean 100 and standard deviation 15. Okay, so the first way to find out is find the usual interval. Find the usual interval, that is the lower fence is equal to 100 minus 2 times the standard deviation, that's 70, and upper fence will be the mean plus twice the standard deviation, that's 130. So the usual interval is from 70 to 130, and you can see 150 is not in that interval. So 150 IQ score, I think I should say IQ score of 150 is unusual. Okay. Now the second method is the method I taught you earlier, is to find C-score correspond to that 150. So the C-score equals to 150 minus the mean, which is 100, over the standard deviation 15. That's 50 over 15. What's that? 10 over 3. That's 3.333. Okay. Now, since the C-score is not between -2 and 2, then that 150 IQ score is unusual. Okay. That's for this 6.3 suggested homework. Oh, hold on, I have a question. What about 3 intervals? Yeah, somebody asked, what about 3 intervals? Hold on. 3 intervals. Okay, the question I get from the chat is, what about 3 intervals? I think I rephrased that to be what about 3 standard deviation away from the mean. So we talk about the mean minus 3 standard deviation, the mean plus 3 standard deviation. I think that's what you refer to. Okay. Here's the thing. There's a special name for that. Okay. There's a special name for that. Data outside of this mu minus 3 standard deviation, mu plus 3 standard deviation is called something with far. Let me find out. Let me find out. Something with far. Not outlier. Not outlier anymore. I mean, you still can call that outlier because it's already outside of twice standard deviation from the mean. Twice standard deviation. I think it's called far out. Give me a second, okay? We don't really use that term, that's why I don't remember. I think it's called far out. Give me a second. I want to find it out also. I'm sorry, I don't find it on internet. What's the terminology? I saw it before, but I don't remember where I saw it. We don't really use it. That's why I don't remember on the top of my head. If you can help me, it would be great. It's nice to know, but it's not 99%. It's not 99%. I think it's 99.7% for the usual interval. So basically, it's like yeah. So for twice standard deviation, you will see. Let's actually do that. Let's actually do that. I want you to know how we get that usual interval. Now, usual interval, as I said earlier, refers to the C-score between -2 to 2. Okay. Now the number actually comes from, instead, the number actually comes from -1.96 to 1.96. That's the actual number. Okay, but because of rounding, they round it to -2 to 2. Now, what I want you to do is to find the probability that the C-score is between negative 1.96 to positive 1.96. Let me ask you to do that. I hope by doing that, we see the reasoning behind it. This is normal CDF. Negative 1.96 to 1.9601. That's a C-score, right? This is a C-score. So that's standard normal. When you compute, this is 0.95000. Okay, now what does it imply? It implies that the probability that not in that interval 1.96 to 1.96 will be the complement 1 minus 0.9500, which is 0.05. That's our 5%, remember? So if we take a look on our standard normal distribution, that 1.96 and negative 1.96 have the area of the tail, this area here and this area here. If we add them together, the sum of the area, the total area is 5%. Now we have said that the event where the probability to occur is 5% or less is considered unusual. Remember, right? Now, so if you are outside of this, to the right of 1.96 or to the left of negative 1.96, then it is considered unusual. Now, then why do they actually change that 1.96 to 2? That's for sake of to compute that easily. Okay? Instead of using ugly number 1.96, they make it 2. Now, after all, when you make it 2, it's slightly to the right. Right? And here, negative 2 is slightly to the left. So the area must be even less than 5%.
Excuse me, Thomas?
Uh-huh.
Can I ask you a quick question? During this computation, I don't know why, but like on my calculator, it keeps showing error. You know, I did the same input, you know, of negative 1.96 and up higher bound of 1.96, 0.0 and 0.1, but like it's showing error for the CDF calculation.
Is it normal CDF?
Yeah, it's normal CDF. On my calculator, yeah.
Okay, can you do the video? Let me see the video.
Excuse me?
Can you video that?
Oh, how do I do the? I mean, okay.
Okay, let me show you what I punched in. Let me show you. Oh yeah. Okay.
Yeah. So I put in the 1.96, 1.96. I put in 0. I put in 1. Yeah, but I when I punch that, you know, it keeps showing error.
Give me a second. Okay. I want to see the view. Do it again, please.
Yeah, for sure. 1 second.
Before you press enter, I want to see your input.
Yeah, I mean, it was fine on like the first couple ones, but on this one is
I don't think you need to use parentheses though.
yeah, but regardless of whatever I
try it again without parentheses.
Yeah, I put in that, and I put and when I put enter,
Uh-huh.
and it shows error.
Oh, wow. Hmm. I wonder what... Okay, I want to find out, because if it happens to you, it may happen to somebody else. Do it again. But right before you press enter, I want to see the notation.
For sure. Yeah, it's a little weird because I tried several times and it's keep
But
showing me.
earlier it was okay.
Earlier on other ones is fine, but on this one is weird.
Uh, did you use negative sign or subtraction sign? You should use negative sign, the one next to enter.
Oh, let me try that. I think that might be the issue then.
Uh-huh.
Yeah, I got it. Okay, I think it
Oh,
was.
okay. Now, I think that's the reason. We need to use the
Yeah,
negative sign instead of the subtraction sign.
yeah, but it kind of worked on the previous ones, so
Oh, yeah. Oh, yeah. Well, anyway, at least we solved one problem. Yeah, I don't want that happen to you when you're at home, or especially during the test.
For sure.
Okay,
Yeah,
yeah.
that was yeah, for sure. Thank you.
Okay, no problem. Okay, let's go back to our notes. Now, yeah, that's the idea behind why we use twice standard deviation away from the mean for to call that usual interval. That's because the C-score corresponds to -2 to 2, but the -2 up to 2 actually coming from the rounded number of between -1.96 to positive 1.96 in the normal distribution. Okay, now I mentioned long time ago about that usual interval. Okay, let me clarify that again. Usual interval in our class is defined as mu minus twice standard deviation, mu plus twice standard deviation, which corresponds to the C-score between -2 to 2. Okay, now, but if you go to Wikipedia or other textbook, the usual interval in other textbooks or in general is defined as Q1 minus 1.5 interquartile range, comma, up to Q3 plus 1.5 interquartile range. Now, interquartile range itself is Q3, the third quartile minus the first quartile. That's interquartile range. Okay. Now you can use this formula to compute the usual interval on our previous questions. Okay. But here's the thing, that the reason I use twice standard deviation away from the mean, it is because of the following. This definition tends to give the same outliers. So if you have some data, okay, okay, we may get different intervals, but when we need to point out who are the outliers, they tend to be the same when, especially when n is the sample size or the population size at least 30. Okay, now since the data we deal with in practice, since the data, the number of data, or maybe I say the size, the population size or sample size, we deal with, in practice is much larger than 30. These definitions tend to give the same result. Now, the reason, I'm not saying that it's always the same. No, no, no. Even if much larger than 30, let's say we have a sample size of 300, they may still give us different interval. Okay, they may still give us different interval, but the difference is not that big. That's one. And when we need to exclude some data, we tend to exclude the same data. Okay, so I'm not saying that they are always the same, but they will be quite similar result. Now, the problem with the other textbook definition, now I'm not saying that's wrong. Okay, in fact, that's the correct definition of useful interval. But for us to find the useful interval this way, we need to first find out the first quartile and the third quartile, which usually not what we have in when we have, let's say, normal distribution, or if we have like 3,000, the size of 3,000, to find the first quartile and third quartile, we need to put them in order first, you know? We need to put them in order first, and then see how many data we have, and blah, 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 blah. The procedure is a lot longer, right? So instead of dealing with the first and third quartile and compute from there, then the first definition is actually easier to use and still provide us the same similar result. Okay, that's why I use this. Now, so if you ask me, Thomas, when to use which one, you can use our class definition of useful interval if the sample size or the population size is at least 30. Then you can use the original, the one that we have in class. Now, otherwise, then you may prefer using this original definition of useful interval. However, one big warning. It is kind of hard to judge if data is outlier based on a small sample size less than 30. It's kind of hard to say. Okay, let me say it again. Using another, let's say we have an illustration. The following, just for example. So we have a quiz score or test score, 25, 75, 90, 95, and then let's say 80. Notice that the sample size is less than 30 here, right? If I put them in order, then it will be 25, 75, 80, 90, 95, right? The median is 80. Okay, so the first quartile is between 25 and 75. And the third quartile is between 90 and 95. That's 92.5. Okay, now interquartile range, therefore, is 92.5 minus 50. That's 42.5. 1.5 of interquartile range is 1.5 times that 42.5. I do it fast, okay? It's approximately 61.75. Now, for the usual interval, therefore, the lower fence will be the first quartile minus 1.5 interquartile range, which is 25 minus 61.75. That's negative 36.75. While the upper fence is quartile, the third quartile plus 1.5 interquartile range, which is 92.5 plus 61.75, that's 154.25. So the usual interval is negative 36.75 up to 154.25. Now the problem is then if you compare to the original data, right? If you compare to the original data, then nobody is outlier, right? Nobody is outlier. But it's clear to see that this 25 is very far from this group here. You see what I mean? Okay. Even though, according to the definition that we had earlier, this is actually the right way to do usual interval. This is the right way to do usual interval. But it's counterintuitive to see that 75, 90, 95, 80. Now, everybody here is passing the class with this, passing the test with this score. 25 is not only not passing, that's actually 1/3 of the lowest score in this group. Do you see that? This is very, very far. This is very, very like a bad outlier. Okay. Now, so this usual interval seems to be the way to do it, seems to be not appropriate. Okay. But you will see the main reason is because the sample size is too small. Okay. So even if we use the usual interval, the definition they said earlier, okay, the definition they said earlier, okay, but because the sample size is too small, it's kind of hard to judge. It's kind of hard to judge if that person is outlier or not. By definition, it is not outlier. From our example here, by definition, it is not outlier. 25 is definitely in this interval, right? But at the same time, you know by when you look at the data, no, something wrong with that one guy, right? Okay, yeah, it's because the sample size is too small. The sample size is too small. Okay, yeah, but when we increase the sample size, you will see this usual interval will behave closer and closer to the way we did it before. Okay, the way we do it before. Okay, now again, this is the correct definition. This is the definition that I use in class, which is more appropriate to use anyway if the sample size is at least 30. Okay, the larger the better, the larger the better. And the reasoning behind that is something I'm about to explain in 6.4, which I will try to explain in a short way, and go on to 6.5. Okay, let me go on to 6.4 and 6.5. 6.4, sampling distribution. Now, this is the one of a very few section in our textbook that I prefer you not to read the book first. In fact, I don't even want you to watch the lecture video because they give you too much details that you lost in details. Now, I will do only one example. I will do only one example to explain what is sampling distribution. Okay, now the main purpose of this, what my explanation here, the main purpose of what I try to explain here is to explain how does the distribution of sample mean behave. Okay, now later on you will see one term that is quite confusing. We anticipate this, something called the mean of sample mean. And what the heck is that? Okay, now to explain that, it takes me a long time. Okay, I realized that in the past, I tried to skip this section and just say it really fast, and I have too many students don't get it. Okay, yes, even after I explain it long way, I still have students not getting it, but at least I try, and students who try to understand tend to understand it. Okay, I need you to help to do things together with me. I will start with let x be a random variable of, let's say, 3, and then 5, and then 11. Okay, now what I want you to do is to find what is x bar, what is the mean, find the mean, and the variance. If you have a data 3, 7, 11. So to compute that, then I need to find the sum of x, which is 3 plus 7 plus 11, that's 21. And the sum of x squared, which is 3 squared plus 7 squared plus 11 squared. I get 179. So the mean will be 21 over 3, right? Because there are only three quantity there. So the mean is 7. And the variance will be m times the sum of x squared minus the square of x, the sum of x over squared. I hope you still remember that formula. That's 3 times 179 minus 21 squared over 3 squared. I get 96 over 9. Let me reduce by 3. Yeah, let me reduce by 3. If I reduce by 3, that will be 32 over 3. And I will leave it like that for now. Okay, so this is the mean and variance of this population X. You can say it this way. Let's say you have outcomes 3, 7, 11. Each one of them has the same probability. So probability to get 3 is 1/3. Probability to get 7 is also 1/3. Probability of getting 11 is also 1/3. Okay, so the mean and the standard deviation will be this. The proper way to compute that is actually by doing the extension of this table. The proper way to do that is supposed to be like this. But I'm just too lazy to go long way. I go short ways. So the x here, the probability here, the output 3, 7, 11, 1/3, 1/3, 1/3, 3/3, and px will be 3/3, 7/3, 11/3, then the sum is 21/3, so the mu is 21/3 equals to 7. And then for the variance, I suppose to extend it again, right? So it should be x squared here, px squared here. This is 9, 49, 121. So this is 9/3, 49/3, and 121/3. When I add 130, 179/3. So the variance is 179/3 minus 7 squared. Okay, but you will get the same number I have. I just do it fast way. I do it fast way because we assume it is equally likely. Now, here's the thing though. Here's the thing. This is the new stuff. So, suppose we do sample of size 2 from X, repetition allowed. So remember our X has 3, 7, 11. Now I want to do sample size 2. I want to do a sample with size 2. Sampling with size 2. So when I sample it first time and second time, okay, the first time and second time, it is possible for us to get 3 and then 3 again, 3 and then 7, 3 and then 11, 7 and then 3, 7 and then 7, 7 and then 11, 11 and then 3, 11 and then 7, 11 and then 11. In fact, this is all possible outcomes when we sample 2 from this population of 3, 7, 11. No other way. It must be only this way. Okay, it must be only this way. Okay, so when we sample 2, there are how many outcomes? There are 9 outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there are 9 possible sample that we can get of size 2 from this original population here. And actually we can compute it simpler way why we get 9. because repetition is allowed, right? The first choice, we have 3 possible options. Okay, the second choice, repetition is allowed, so I can choose one of these 3 again. That's how we get that 9 possible outcomes. Okay, fundamental theorem of counting, fundamental principle of counting. Okay, so these are the possible samples. There are 9 of them. Now, what I want you to do next is to find the sample mean. Okay, because it's size 2, I write 2 underneath here. That's for sample mean of size 2. Like for example, the first possible sample, 3, 3, the mean will be 3 plus 3 over 2, that's equals to 3. Okay, the second possible outcomes, 3 and 7, the mean of those 2 will be 5. And so on and so forth. Okay, let me ask you to try this. Finish the other 7. I give you 1 minute. Okay, let me continue. Then the third one will the average will be 7. The fourth one, the average is 5. And then 7, and then 9, and then 7. Oops, what happened? And then this is 9, and then 11. Now, so we can say that the random variable of the sample means of size 2 are now 3, 5, 7, 5, 7, 9, 7, 9, 11. They are all equally likely, because each one of these possible outcomes here, are equally likely. Therefore, each one of these possible outcomes here will also be equally likely, right? Okay. Now instead of computing it the correct, quote unquote, the correct way, I would just do the fast way, because they are equally likely anyway. So I will compute the mean of this X bar as the sum of all these numbers. You can use your calculator to compute that, and I will also compute the sum of X bar squared. Okay, let's see, 3 plus 5 plus 7 plus 5, that's 20, 36, 43, that's 20, that's 63. And then the sum of X bar squared will be 3 squared plus 5 squared plus 7 squared, all the way to the last one plus 11 squared. I get 489. So the mean of this sample mean, now you see what I mean by this mean, the mean of the sample means. When I sample the size of 2, these are the possible outcomes. Okay, these are the possible outcomes. So the sample mean, when you sample from this 3, 7, 11 here, when you do the sample mean of size 2, we have these possible outcomes. Okay, now the mean of that sample mean The mean of that sample mean is 63 over 9, because there are 9 elements in there. That will be equals to 7. Now, the distribution of sample mean, let me write it in red. The distribution of sample means is now called sampling distribution. Okay. Now, the reason they call that sampling distribution, I believe, because they just don't want us to get confused with distribution of sample means. You know, when we do sampling of size 2, like in this case, okay, we have possible samples coming up. There are 9 possible possible outcomes for the samples, right? Now, this is all the possible sample though. So in some sense, even though they are the sample of size 2, because this list is all possible outcomes of sample of size 2, then we consider this a population. This is the population of all possible outcomes of the sample mean of size 2. That's why I use mu here. Okay, that's the mean of all possible outcomes of those possible samples. Okay, now the mean of the sample mean, the mean of the sampling distribution is 7. Now, I want you to realize that this is the same to the mean of the original distribution. The mean of our original distribution is 7. Okay, I use subscript X here to emphasize that's from the original distribution. Okay, I use subscript X bar here to show you this is the mean from the sample. Now, the first conclusion we have is the mean of the sample is the same to the mean, I think I have to say it correctly. The mean of the sample means is equal to the mean of the original distribution. Now, how about the variance? The variance of the sample means, let's compute this. The n will be 9. There are 9 possible sample means times 489 minus 63 squared over 9 squared. I get 432 over 81. Let me reduce by 9. I get 48 over 9. Okay, which I can reduce further by 3. That's 16 over 3. Now, the reason I don't want to make it decimals so that you can see better how we can compute it a lot faster. Now, compare that to our variance of the original distribution. The variance of the original distribution is 32 over 3. The variance of the sampling distribution, the variance of the sampling distribution is 16 over 3, whose relation compared to the original variance is the original variance divided by the sample size 2. Okay, this is 32 over 3 divided by 2 because I sample size 2. Okay, that's how I get that 16 over 3. Now, if you have a chance, if you don't really get it, try to go over this lecture video again, which I will put on YouTube. Okay, but let me just do the summary. Here's the summary. Basically, we have this sampling distribution. That says let X has mu sub X and sigma square X, whatever those numbers are. Then the sampling distribution of size n has mu sub x bar equals to the same mean of the original distribution, and the variance of the sample mean is equal to the original variance divided by the sample size n. That's the conclusion, the summary I need you to get from this 6.4. Okay? Now, don't worry, we will encounter this again with some concrete example. I'll write it down first. Let's do some example. Let X be distributed in a way that the mean, let's say, is 72, and the standard deviation, let's say, is 10. Now, then, what will X bar 3? How will X bar 3 distribute it? Now, we don't know how it will distribute it, but we can find the mean of X bar. The mean of X bar will be the same. The mean of X bar will be the same. While the variance of X bar, the variance of the sample mean, will be the original variance divided by sampling size. Is it okay? So we work hard for how many minutes? Like around 20 minutes. We work hard using this example. Just one example takes us 20 something minutes just to come up with this conclusion. And from this conclusion, we do this example, which we did in 1 minute. Now, if you go over our textbook 6.4, our textbook actually did like how many examples? Our textbook did a lot of examples there, and rightfully so, because if we take a look on the details, we can apply this to a lot of different distribution. But even if we apply to different distributions, a lot of different distributions, the distribution of sample mean always follow this formula. Always follow this formula. Okay, always follow this formula. That's why I'm not really interested in finding if doing a lot of examples. I do only one example, like one long example here. Okay, only one long example here. And then more on short examples. Let's see another one. I give you, let's say, 1 minute to do this. Let X be binomially distributed with n equals to 30 and p 0.4. It's binomial distribution. So what is the mean? The mean is NP, which is 30 times 0.4, that's 12. And the variance is NPQ, which is 30 times 0.4 times 0.6. The Q is 1 minus P. Okay, so that will give me 0 point, I'm sorry, not 0 point, it's 7 point. That will be 7.2. Okay, then what can we say about X bar 4, let's say? Then X bar 4 will be distributed. We don't know the style of that distribution, but we know the mean of that X bar will be the same 12. Will be the same 12. While the variance of the sample mean, sample mean will be the same variance to the original distribution divided by the sample size 4. That's 1.8. That's it. Just like that. Okay? Now, I go on to 7.5 because 7.5 is actually continuation, I'm sorry, 6.5, because 6.5 is basically continuation from there. Now, what is 6.5? 6.5 is central limit theorem. 6.5 central limit theorem. I will write it in short CLT. Now, central limit theorem says the following. There are two parts of central limit theorem, but they are actually quite similar. The first part, if X is normally distributed with mean mu sub X and variance sigma square X, then X bar n will be normally distributed with the mean equals to the original mean and the variance equals to the original variance over sample size n. If you want to read, if you don't like my notation, I welcome you to read our textbook on how it describes central limit theorem on page 281. See if you like it. If you like it, then go ahead, use that one. Okay? But I don't like it because it takes half a page. Like If too much wording, you say it's confusing. Now, I try to make it shorter, less wording, more notation. Of course, it still can be confusing. What's the issue? The issue is with understanding. It's not about, is it like a lot of wording or not? It's about understanding. Okay? Now, so try to understand the notation here. Try to understand the notation. It's on page 281 if you like wording. Okay. So, Thomas, this is central limit theorem, but I feel like we have seen something. Yes, yes. It has a lot to do with sampling distribution we learned earlier. What sampling distribution says earlier was this. Sampling distribution says if x has the mean mu sub x and variance sigma squared x, then x bar n must have the mean the same to the original mean, and variance of the sample mean will be the original variance divided by n. That's what we learned last section in 6.4. So Thomas, so what's the difference between what we learned last section to central limit theorem? The difference is here. When it comes to sampling distribution, we don't know what is how the random variable be distributed. We don't know how the random variable be distributed. So the sampling distribution also has unknown distribution. We know the mean, we know the variance, but we don't know how it is distributed. Is it binomial? It is normal? Is it Poisson? We don't know. Okay? If we don't know the original distribution. Okay? Now, in central limit theorem, it says something stronger in the hypothesis. Suppose we have a distribution that is normal. Okay, if x is normal, then the sampling distribution will be normal too. Okay, now what we have here and here are from sampling distribution from last section. The one new for us is this. Okay, notice that in 6.4, in the examples I give you, we can only find the mean of the sample mean, right? The mean of the sampling distribution and the variance of the sampling distribution. That's all, but I cannot compute any particular probability. Now, in 6.5 now, suppose we start from normal distribution, then the sampling distribution will also be normal. Okay? Now, let me save some, keep some space here. Let's do some example. Let's do one example. Let x be normally distributed with mean 100 and standard deviation 15. So the variance is 15 squared. Okay. Now you remember this is the standard. This is the distribution of IQ score, right? Okay. So let's see. Suppose I pick one person at random. What is the probability that person's IQ is more than 110? Now, let me ask you to compute this in 1 or 2 minutes. Okay, this will be normal CDF 120 E99. The mean is 100. Standard deviation, not variance, not variance. When you do calculator, they use standard deviation 15. I get 0.09121. Thank you. Now, what's the difference to what can we do with this sampling distribution? Suppose I want to sample 3 people at random. So I sample 3 people at random. What is the probability that their average IQ? What is the probability that their average IQ, the average of 3 people's IQ, is more than 120? Let's see, by central limit theorem, x bar 3 will be, see, it's normally distributed, right? The original distribution is already normally distributed, then the sampling distribution will also be normal. Now, once it is normal, then we can use normal CDF. Okay, what's the mean? The mean will be 100. How about the variance? Then the variance will be 15 squared over 3. Now, so if I want to compute the probability that the average IQ of 3 randomly selected people that will to be more than 120 will be still normal CDF, because x bar 3 is normally distributed. What is the mean? I mean, the left bound is 120. The upper bound is E99. What is the mean? The mean is 100. However, how about the standard deviation? Standard deviation. The standard deviation will be 15 over square root of 3. Okay, don't forget that this position is for the variance position. Is 15 squared over 3. So the standard deviation of x bar will be the square root of that. 15 over square root of 3. Do you see something new there? The answer is, according to our friend Esteban, is 0.01046. Okay, so the probability to get somebody whose IQ score is more than 120 is 0.09 approximately. The probability to get 3 people whose average IQ is more than 120. So on average, 3 people's IQ is more than 120 is 0.01. Of course, it is harder, right? It's harder. Why? Because more than 120 is away from the mean, right? Okay, more than 120 is away from the mean. Oh, let me check Sorry. Yeah, that's correct. Yeah, that's correct. Yeah, that's correct. Yeah, I get 0.01046606. Yeah, if I round it to 5 decimal places, it gives me the same number that you gave me. Thank you, Esteban. Okay, now let's take a look. What is the effect of sampling distribution to the normal distribution? What happened is this. What happened is this. Where's my... Now, this is the normal distribution we have. Okay, let me enlarge that. Let's say this is the distribution of X. This is the distribution of X. What happened with sampling distribution, if it were normally distributed, the standard deviation, the variance of sampling distribution will be the variance of the original distribution divided by n. Okay, this means the curve is skinnier yet taller. Okay, so approximately it looks like this. If you divide by, let's say, n by 2, let's say, then the curve will look like approximately like this. I just try to show you that it gets skinnier. Okay, it gets skinnier. Now, so in our question earlier, let's say this is 120, right? So this is for IQ score 120. Okay, so only one person, for us to get one person with IQ score more than 120 is 0.9 approximately. But to get 3 people have average IQ score more than 120 will be smaller. Okay, because now the probability gets more concentrated around the mean. You see? Okay, now, so if our interval includes the mean, if the interval that we want includes the mean, the probability will get higher. Okay, but if the interval does not include the mean, then the probability will get smaller. Okay, let's take a look again on this example. I wonder if you already write it down. If not, please write it down, because I'm about to go to word problem. Okay, let me continue. Let's take a look on page 288, number 8. I'm sorry, number 6. Number 6. The problem starts again from the distribution of a woman's height. Let X be a woman's height. We know that if you read from the previous page and what we had before, a woman's height is normally distributed with mean 63.6 and standard deviation 2.5. So I use 2.5 squared there for the variance. Okay, now 6A. If one woman, only one woman, is randomly selected, what is the probability that her height is greater than 63 inches? Probability that her height is more than 63. Now we did this routine earlier. I hope enough number of time. Okay, so this will be normal CDF 63 E99 63.6 2.5. Lower bound, upper bound, the mean, standard deviation. When I compute that, I get 0.59483. Part B. If 100 women are randomly selected, so 100 women are randomly selected, find the probability that they have a mean height. So you have a sample of 100. What is the probability that the mean height is greater than 63? Probability that X bar 100 is more than 63. That's normal CDF. Okay, you see, if X already normally distributed, then X bar N will also be normally distributed, with mean the same 63.6, and the variance 2.5 squared over N. Okay, so here, if you have 100 people, 100 women, what is the probability that the average height of these 100 women is more than 63? That will be normal CDF 63 E99 63.6, and this is 2.5 over square root of 100. Because this is the position for the standard deviation, okay? Now then, when I compute that, I get 0.99180. Okay. Now, anybody wants me to show how to use the how to punch it into calculator? You can punch this in your calculator for the standard deviation part. Okay, you can use this. You don't need to actually compute 2.5 divided by square root of 100 yet. Okay, you can just plug that in. So on your calculator, let me show you. Okay, let me show you. Give me a second. Where's my calculator? Boom. I want to do normal CDF. Okay, the lower bound is 63. The upper bound is E99. Oops. Okay, the mean is 63.6. Yeah, the mean is 63.6. And then the standard deviation is 2.5 divided by the square root of 100. Then I press enter. You see what I mean? Okay, that's how I punch that. Let's go back to our note. Okay. Suppose I have extra question. You try this one. You try this one. What is the probability that if I sample, let's say 6 people, what is the probability that the height is more than 60? The average height to be more than 60. Now, you do it. I give you 2 minutes. Okay, let's continue. This is normal CDF. Left lower bound is 60, upper bound is E99. The mean is 63.6, and standard deviation 2.5 over what? That's right, square root of 6. Right, that square root of 6 comes from the sample size. Okay, now then when I compute that, let's see. Oh, I get 0. Big number, 99979. Okay. Now, that's the first part of central limit theorem. Let's go back. That's the first part of central limit theorem. If the original distribution is normal, then the sampling distribution will be normal. Now, the second part here is the case when the original distribution is not normal. We just know that the mean is mu sub x and the variance is sigma squared x. Okay, in other words, x is not normally distributed. Now then, x bar n, strangely, is still normally distributed, with the mean the same to the original mean and the variance is the same to the original variance over n. So basically, they have the same conclusion here, the same conclusion here. The same conclusion. But you see that the original distribution was not normal, right? Okay, but the x bar n will still be normal as long as the n is greater equals to 30. okay, for n greater equals to 30. So even if the original distribution is unknown to be normal or not normally distributed, then the sampling distribution will still be approximately normally distributed as long as the sampling size is at least 30. Okay, now I have to say that this is not always true. No. There have been some very rare situation in which the x bar n is still not normally distributed, even if the sampling size is more than 30. But that situation is very rare. It's very rare. Okay, such that at your level, we can say that in general, as long as the sampling size is more than 30, then the sampling distribution will be approximately normal. Okay, so how do we use this? Let's go down, go to our node. Suppose, for example, that x has the mean of, what's that again, 72, and the variance to be, let me see, what did I use? 10. The variance to be 10. Okay. Now suppose I want to know how x bar 15 distributed. Then we only know that mu x bar equals to 72. Okay. Sigma squared x bar equals to 10 over 15. Okay. But since 15 is less than 30, the n is less than 30, then x bar 15 is not normal yet. At least it's unknown. Okay, we cannot use central limit theorem yet because the requirement that the sampling size to be at least 30 is not being satisfied. Now, however, if somebody asks, okay, how about if I sample 150 people? If I sample 150 people, now notice that the sample size 150 is already more than 30. In fact, that's a lot more than 30. Therefore, we can now use the central limit theorem that the sampling distribution of size 150 will be normally distributed with mean 72. I think I want you to use another color. Sorry, don't use yellow. With mean 72. Okay, and the variance will be 10 over 150. Because the sampling size is more than 30 already. Okay, so then we can answer this question. What is the probability that x bar 150 is, let's say, less than equals to 75? Then this will be, because it's normally distributed now, it's now normally distributed, right? So I can use normal CDF negative infinity, negative V99 to 75. The mean is 72. The standard deviation will be square root of 10 over square root of 150. So normal CDF, negative infinity, negative V99, up to 75, which means 72, and standard deviation of sampling distribution is also called standard error. That's square root of 100 divided, square root of 10 over 150. I get 1. Yeah, I get 1. Standard deviation of sampling distribution is also called is also known as standard error. Okay, yeah, but when I compute this, I get the probability is 1. Now, let's do one more example before I let go. Let me do one more example. This time, let me pick questions from the book. 6.5. Which question is good? Page 290. Let's see. Page 290. Number 20. I randomly pick questions. Okay. Under older FAA rules, airlines had to estimate the weight of a passenger as 185. Current rules require an estimate of 195. Oh, men are normally distributed. Oh, no. I don't want that to be normally distributed. I don't want that to be normally distributed. Let's see. I try to find a question that's not normally distributed. Number 11. Sorry. Number 11. I need to change it to number 11. So that's page 289. Yeah, because once the original distribution is normally distributed, then regardless the sample size, so you see, if the original distribution is already normally distributed, then for any sample size, regardless the sampling size, then the sampling distribution will be normal. I try to find an example where the original distribution is not necessarily normal. Okay, yet because the sample size is at least 30, then the sampling distribution becomes normally distributed. Okay, that's the reason I pick another question. And I see number 11 is the situation that we like to see. Number 11, assume that cans of Coke are filled so that the actual amounts have a mean of 12 ounces and standard deviation of 0.11 ounces. Okay, so notice that it doesn't say that the volume, the actual amount, is normally distributed. Okay, it doesn't say that. So let X be the amount of Coke in a can. Now then, X is distributed with the mean equals to 12, and the standard deviation, not the variance, standard deviation is 0.11. Okay, now part A, find the probability that the sample of 36 cans will have a mean amount of at least 12.19. The probability that the sample of 36 cans has averaged more than at least 12.19. Now, we know from central limit theorem, because the sample size is now 36, which is more than 30, then we can use central limit theorem that X bar 36 will be now normally distributed with the same mean 12 and standard deviation 0.11 squared. That's the variance of the original distribution divided by the sampling size 36. Okay, if I go back here, then the variance of the original distribution is 0.11 squared. Now then, how to compute the probability here? This is normal CDF, okay, of 12.19 up to infinity because it's greater than 12.19. Okay, the mean is 12. The standard deviation will be the original standard deviation over the square root of the sample size. Okay, you can imagine if I do the square root of this thing here. The square root of this thing. Okay, then what do I get? (12.19, infinity, 12, 0.11 over square root of 36. We get 1.85385 times 10 to the negative 25. I wonder if you get the same result. Yeah. If I round to 5 decimal places, that's basically 0. So it's impossible if you take 36 cans and the average amount of Coke in that can is more than 12.19. Yeah. The probability is so small that it is considered to be impossible. Okay. Now, let me do one more problem. I would like to do one more problem if you don't mind. But this is a problem that I don't think you can find in in the book. I'm not sure. Okay, I'm not sure. But let's say the following. So instead of doing part B, I will call that variation. Okay. Find the probability that total amount of coke in 36 cans is less than 500 ounces. Now you have 36 cans. 36 cans. Total 500 ounces. So the average per can is total less than 500, right? So the average per can should be less than 500 over 36. Is it right? Now, so the probability that the average of these 36 cans is less than 500 over 36. Okay, that's equals to, now, I mean, we are done with the setup. You just use what we did earlier. Normal CDF, okay, negative infinity, upper bound 500 over 36. The mean is 12. The standard error is 0.11 over square root of 36. That's negative infinity, comma 500 over 36, comma 12, comma 0.11 over square root of 36. I get 1. Okay, basically we are saying that the probability that the total amount of coke in 36 cans is less than 500 ounces, the total is less than 500 ounces, is equal to 1. Because for that to happen, the 36 cans total less than 500, it means the average per can will be less than 500 over 36. Okay, now I already post a take-home quiz that you need to turn in next week. I strongly suggest you to turn it in before then, a couple days earlier if possible, so that you can focus on your test next week. Okay, the reason I give you that take-home quiz so that you still study for this normal distribution. Okay, see you then next week.
Excuse me?
Uh-huh.
Yeah, I just want to ask, does this quiz overlap with the material that's going to be on the test?
No, actually a good question. Your test tool, give me a second. Let me stop recording.